So you've already met our speakers today or heard from them. I just want to do a quick introduction of the three other people. John Brennan is a professor of linguistics, second from the far right, from the far side. Peter Railton is Gregory S. Kafka Distinguished University Professor of Philosophy, who's the fourth from that right. And then Rada Mihalcea, who is a professor of computer science and AI lab director, two steps from me. So this has been an amazing day of amazing talks. Before we actually begin the panel, I just want to acknowledge the hard work of Rachel Miller and the Weinberg committee that went into organizing this wonderful event. So let's thank Rachel. So as I said, there'll be sort of three things. One, I will basically maybe seed a question. Then I really want to encourage the panelists to talk to each other for a while. If they don't have enough things to talk about, we will perhaps get a chance to have the audience ask questions. So do think of questions. So just to mix it up a little bit, the three people on the panel who didn't tell us about their thoughts, I'm going to ask a question at least for them. So one of the things that Rick Lewis, in introducing the symposium, asked was, what are some problems that belong to this shared frontier of AI and cognitive science? And we heard a lot from all the speakers about some of those, but I would like to give a chance to John, Peter, and Rada to give us maybe one example of a problem that they feel might not be studied enough, or is incredibly important, or is a sharp problem to focus on. So let's start with John, then Peter, then Rada.
Thank you, Satinder. I did not expect to be the first voice here. I'm a linguist, so my answer is going to be connecting to language, which we heard a little bit about today. But of course, I think we didn't hear enough, and so there's some real hard problems in language. I think we might all acknowledge. And what's interesting is these problems have been recognized almost since the beginning of modern linguistics. So the way a lot of the generative approaches to linguistics have framed their problem has been in response to some of the very interesting theories of learning that were developed, that we saw some reference to today. That the theories of learning developed to solve those problems of induction that Animal showed could not stand up to some of the problems that the child faces when learning language. So I think linguistics furnishes a set of hard problems that are useful. I have a list, but I'm not going to go into it. But useful test cases. Some of these were recognized in the 50s and 60s and 70s. Some of them more recently. But a set of hard problems that I think would be nice to see put up there amongst the other challenges we're seeing as compelling challenges.
Peter.
Is this on?
It is.
Yeah. Thanks very much. This has been very illuminating for me, and I really have no business up here, but I'll do what I can as a philosopher. One hard problem is the representation of intuitive knowledge generally. Especially interesting to me is the representation of intuitive moral knowledge, which involves social knowledge, involves causal knowledge, theory of mind, and so on. But one thing that struck me, and perhaps people can comment on this, is that a lot of our discussion, even the discussion of the child as a model, was discussing a sort of asocial development of minds that we're going to release into society. And we wouldn't think that was a good idea with infants. Well, I think this is a good idea with machines. And I say this with a sense of some urgency because the extent to which these systems are entering into our society and making decisions, entering into interactions that affect people very much is expanding very rapidly. And I would like to know if are there enough resources being devoted to this question of what it would be like to acquire the kind of information that would make it possible for such machines to do something like intuitive moral thought, and then to use that in their behavior, because they're going to use something else if the intuitive moral thought is not there.
So one thing that I've been quite passionate about lately is how we can use information about people for building better computing models. And a lot of the work that has been happening at the intersection of computing and cognitive science, or even more broadly social sciences, I think has been going in the direction of using computational methods for maybe reaching a better understanding of social science problems. And I think there is a lot of room for going also the other way around. And specifically in computer science and in AI more specifically, there has been a lot of work on models that sort of are one-size-fits-all models. Thinking of natural language processing, which is my area, we have, for instance, part-of-speech taggers, or language models, or parsers, and whatnot, but they are generic. They are not necessarily adapted to specific groups of people, or maybe specific beliefs, or specific values, behaviors, and so forth. So one thing that I would say falls in this frontier of AI and cognitive science is this idea of using information about people to build better models. And that could be natural language processing, it could be social network analysis, it could be computer vision and other problems within AI that could be more informed by cognitive science.
Good. Does anybody else feel compelled to add a problem?
I have something to add to follow up on those issues that raised. Yeah. Oh, thank you. Yeah, I completely agree that that language has been. I think. Well, the reason I didn't talk about it is that it's really hard. One interesting thing that's been going on at DeepMind is trying to investigate language acquisition in settings where it can be grounded. So it's not learning language from text corpora, but also learning in a sensory motor environment, and that changes the topic the way that embodied vision changes the topic from vision without embodiment. But actually, the main thing I wanted to speak to was moral intuition, and just to say that. My perception is there's a great deal of interest in the reinforcement learning community in multi-agent situations, both from the point of view of learning to model other agents, this theory of mind perspective, but also learning to coordinate, learning to compete. And that setting raises irreducibly, new issues over and above settings where you have a single agent battling a video game. But one thing that I've actually only learned recently is people here can correct me if I've got the names wrong and so forth. But my understanding is that it's been shown, it's been formally proven in behavioral economics that once you're in a multi-agent setting, it's no longer possible to specify an objective function that's defined purely in terms of one scalar, the way that we usually do in reinforcement learning. Because now you have to take into account things like equity and peace, and it's inherently multidimensional. And even independent of that, it brings us back to an issue that I heard Rich bring up, I think in just a private conversation earlier, about reward function design. This is something that I think people don't appreciate in the broader community about reinforcement learning, is that we have to, when we build RL systems, we have to say what the reward function is. I don't know any other way of getting to that reward function. And in multi-agent settings where there are these complex considerations of what's good for the community, that's raising all sorts of interesting.
So I want to I'll have one question, and then I want the panelists to ask each other questions. So this is a personal sort of question for me, because I'm puzzled by this genuinely, which is we talked about all these, or many human capacities, many human capabilities, intuitive physics, moral understanding of things, theory of mind, predictions, all kinds of things like this. There's a certain clarity to the view that, let's say, Rich presented, which is that there is this reward signal, and we are trying to optimize a reward signal. Things fall out of that we as observers might look at and ascribe whatever linguistic terms we would use to describe that phenomena. It's a little hard for me to understand or figure out how explanations or theories for each of these sort of phenomena that have been talked about, how do we figure out we're getting them right without that clarity that Rich's point of view provides? So like intuitive physics, what's a theory of intuitive physics? How would we know we've accomplished it? what does it even mean in an artificial agent, or something like, or moral understand? Yeah, good. I've asked my question.
I don't. It depends what you mean by getting it right. But if you mean the usual scientific thing, then you do the usual thing you do in science. You do a lot of experiments. You build multiple models. You test them against each other. You iterate. You find ways into things where maybe the models don't make different predictions, but then you find ways to make different predictions and do experiments that test those. You build new models, right? I mean, if by getting it right you mean that, coming to a more right understanding of how human intuitive physics works, then you do science. And now, I believe in a unified cognitive science, which includes AI, where part of getting it right is that your models, and I think this is very much shared with other speakers, your models have to actually do the engineering work for you. They have to be the kind of things which, when you give them the data that come in to a robot, for example, they should do the things that you want the robot to do, and actually could be deployed in robotic settings even. So intuitive physics is a great example for that, because it's a very important frontier area in robotics.
So good. So take Kristen's beautiful work on going from pixels to some kind of understanding of the visual world, and then be able to answer questions about classification and so on. So would that, it works, it learns from data, would it constitute a satisfying theory for a cognitive scientist?
You're saying for specific...
Or take DQN playing Atari.
So for a long time, psychologists didn't do anything like from pixels. I mean, only very low level sensory psychology worked with raw images. And a lot of it was because people didn't know how to study build the right kinds of intermediate representations. But right now, if I look around the labs near mine and my own lab, and many others in cognitive science, there's a real value in the community in psychology, in perception or cognition, but let's just say perception, and what's called image computable models. So around MIT, if you just have a word model and it's not image computable, then you get bashed for that, right? So our models for intuitive physics, I didn't emphasize this, and there was, there's only, I know I went on a little too long and I could have gone on for a lot longer, but in some of the slides I skipped over, we build image computable models for intuitive physics that use neural networks to map from images to the scene representations that the physics engines work on. And it's very much the same kind of thing, I think, that that you're doing in your work, and one of those students was even thinking about doing a postdoc with us. And so I think they're part of the same broad enterprise. I think it's strictly better if we have models for things like intuitive physics that work with the kinds of sense data that infants, monkeys, and robots all get.
Good, thanks. Kristen, you wanted to add something, and then Rich, I'm sure you have a question.
Yeah, I was just going to say that I think part of your question is what is the it, right? So you're saying to demonstrate it works, there's also the question of scope, and where does intuitive physics or some other sub-concept start and end? And for this group, maybe the answer is, well, human capability. But my understanding is that's also very hard to scope out. And so declaring success on a portion of it, whether it's image recognition or new frontiers for intuitive physics and things, is part of the challenge, is knowing what that scope is. Because once we know it, I think the scientific and experimental approach to demonstrate and compare and so on, we have a handle. But yeah, my sense is that's a good question for us. Yeah.
So now you guys get a chance to ask each other questions. So Rich is going to start. Looks like.
Well, I just thought I'd take a turn here. I wanted to answer the first question a little bit about what are the problems come up. I think this is one thing that Josh got exactly right, that the key problem is how do you model the world and plan with it. And that's like the big thing that we don't know how to do so far. And if we could do that, if we could learn a model at scale, like with deep learning, learn to model the world and then plan that model, we would have much more capable systems. We would be, I think, approaching something you might really call intelligence. The second thing I want to do, having grabbed the microphone, is get my question in for Kristen that I've had ever since her talk, which is she described all these wonderful ways in which actions and time could be brought into visual recognition, and that's really special, a new direction that I'm really excited about. And so that's the main thing. I'm just all excited about this, but I'm saying to say so it's still recognition. And I wonder if that ends up being a block, because recognition is sort of an atemporal. I mean, really, the output should be something more like an action itself. And so does that ever become a roadblock to this direction?
Right. So I think, yeah, there are broader challenges and beyond recognition. And I mean, for one, take activity and understanding that is, and I don't think this is exactly what you were getting at, but one that makes me think of like activity over time, especially a composite activity, and not an instantaneous understanding of what's happening right now, but kind of a series of events that will compose an event, a series of activities that will compose an event. But also I think what is a challenge for us on the computer vision side or AI side was, I mentioned, I think I even described recognition as comfortable in our field, and not that it's perfect, not by any means, but it's also comfortable in the sense of evaluation and learning. So related to what I said a minute ago about scope, right? We are trying to think of, preparing agents, visually intelligent agents for tasks that are to be defined in the moment. But as an engineer or someone, developing things, you have to have a concrete means to evaluate, and recognition is not the only one. But being able to have things that can generalize to tasks, well, you still need to enumerate those tasks once you're demonstrating it.
Questions from other people in the panel?
I wanted to come back to the question, the idea that the value function or the goal itself has got to be part of the learning system, and systems have to acquire new goals or unlearn goals that are, for whatever reason, inappropriate or infeasible or whatever. And it seemed as if many of the models add in the goal by hand, so to speak, or through something like a scoring system. Planning, of course, involves forming sub-goals and then revising those and so on. I'd be very interested to hear, maybe especially in these interactive cases, about mechanisms that people have looked at for something like goal revision and goal specification.
Well, I'd like to try to answer that just a little bit, or just add some clarification.
Yeah.
So we have this thing in reinforcement learning we call it the value function, and so it kind of sounds like values in human values, and it's not unrelated. It is sort of, it has a particular definition, as Rick or Matt pointed out. It's defined as the expectation of the future reward summed over an interval discounted in a certain sense. And so that's a clear idea. And now it's the sum of the rewards, and the rewards are the reward signal. So where do the rewards come from, and why should the agent try to be maximizing those rewards? Okay. Well, sort of the idea is, I think it's a very natural idea, is that you can want something because it gets you something else, and that something else you might want it because it gets you something else, and there's a sort of infinite regression, perhaps. But at the end, there's got to be one thing that doesn't have a reason. It's just you want it because you want it. Okay, and that's what the reward is. The reward is the thing that has no other explanation. Okay, and so in a game of chess, we make checkmate. Winning the game is rewarding, and in the Atari games, points are rewarding. And so the designer determines the reward signal, as Matt was saying. But now we only have these two things. We only have the reward, and we have the value. The value learned as an estimate of the future reward. We don't have a special thing for morality. We just have values. And so this is the question that I'm always wondering. Do we need a special thing for morality or for multi-agent interactions or whatever, or is it enough to have just the two? It's a deep, fascinating question.
So I agree, these are deep, fascinating questions, very good ones. And I think that the idea of, I mean, if we make a list of top ideas that have proven their worth over time, the general idea of, you know, you call it the utility calculus in all its forms is definitely one of them, right? The idea of utilities as a way to think about goals and values, and the value function in RL is a beautiful idea. I love talking about it. So while I'm sometimes critical of RL as a way to build AI, the idea of the value function is incredibly deep, conceptually and mathematically, and certainly important. But at the same time, yeah, I think I'm just sort of agreeing with the general sense here that this toolkit of utilities and value functions, it sounds kind of like values, but it's not. And how do we go from that toolkit to all the things that, let's say, in particular, philosophers have been telling us are important for centuries about values and goals is a really interesting open question. I guess I would just say a couple of things on the frontier from where I see it. One is that you know, well, I mean, Peter, you know this because we presented some of this in the moral learning workshop that you've done here. I mean, we've actually been working on, and a number of people are working on sort of extending the toolkit of utility theory to capture some of these higher order kinds of things, like what Matt was talking about, notions of equity and fairness. And you know, I think we're just scratching the surface of this, but I think we're gonna start to see, in the same way we've seen, you know, these probabilistic programming languages, you could call them like utility programming languages, like ways of describing abstract structures of utilities that will be compelling ways to think about or hopefully more somewhat useful at least, compelling small next steps to think about these higher level issues of human values and morality. But even basic notions of like a goal, I mean, I agree with Rich saying, like, where does a goal come in? Like a goal you know, it's some kind of a symbolic concept. I mean, here I would say, though it doesn't fit into the utility theory toolkit, I think it's an important part of the human intelligence toolkit. And I would look not just to morality, but to language, right? So again, I'll defer to linguists to talk about this. But if you look at, you know, linguists will often tell you that the basis of meaning at the sentence level hangs around verbs, right? Verb is the heart of a sentence. And you're not going to understand what verbs mean and how they work unless you understand goals. And the way we talk, it's both how we talk to each other, but also how we come to many of the goals we have. It's through language. So I think that's just one of many places where language provides a window into cognition that really makes goals important. I don't think they're just epiphenomena or even emergent phenomena. I think they are first-class phenomena that we can reverse engineer.
Do the linguists want to add?
Not on that particular point. I did have one question, I guess, maybe if I could ask the other members of the panel. And I think it comes out of the discussion so far, which is something about what counts as success. What counts as success as engineers, as scientists evaluating these models? When is a model a successful model? And we saw several graphs. I'm thinking the Atari graph that we saw several times because it's so beautiful and so compelling a result. And the performance is so good. But I wonder if that performance is what we should be seeing as success. I want to get other people's opinions on this. And in particular, I'm thinking of a video I show my undergraduates in the first day of class. And if there are any in the audience, you will be rolling your eyes at this point, where we look at IBM's Watson just wiping the floor with the human players of Jeopardy, beating them by thousands and thousands of dollars and this is in 2011, with this question answering system. And so this is an amazing result. But what we see in a 4-minute clip is just how when Watson makes a mistake, it doesn't make them very often, but when it does, they are phenomenally bad mistakes. Awful. Mistakes people would never, you or I, and I'm never going to be on Jeopardy, would not make. And so I wonder about the kind of mistakes that we see in our systems, even when they're being more successful in say, achieving a particular kind of goal on a video game or some other task. When they see the mistakes, what kinds of mistakes do they take, and how can we use that to better shape our ideas of these models of intelligence? That's the question.
So just to respond to that quickly, I think it's a great point, and it's a classic way that psychologists have often studied human knowledge or processing is by looking for patterns of error in addition and patterns of success. And we do this in our models, right? I think we often, the high level first point is often, look how successful this is, because we're trying to explain something that humans do that previously no machine system or model or equation has done. But then if you want to dig into that, beyond that, and say, okay, but is this doing it the way humans are doing it? Often the patterns of failures are more diagnostic of that. And I know I didn't show this like in the intuitive physics work. One of the things that we've done with these models is show how they can explain and make sense of some classic kind of illusions where people, for example, misperceive physics, or they even motivated us to discover a new illusion, the kind of stability illusions. I mean, people are familiar with this if you've ever like seen or participated in things like rock stacking. Like it's often done at the beach. I don't know if they do it at the shore of the lake here, but people will stack up rocks in ways that look like they should be falling over, but they're actually stable. Our model basically has an explanation of why we tend to see things as illusorily stable in these cases. As a result, basically, it's a kind of probabilistic inference. Genetically, even though this particular configuration is stable, it's because of noise in your system or uncertainty in many aspects of the object shapes and states and physics, the actual rational probabilistic inference is it should be falling over. And that makes some other predictions which you can follow up on. Like it predicts that you should have stability illusions in one way but not the other.
So Josh, let me interject and give, maybe change the question a little bit, but there's a lot of focus these days on trying to look at, say, through generative adversarial networks and other things as to where our high-performance systems fail and what kinds of mistakes they make and all of that understanding. But is that any different from the example you pointed out, where people who had never played video games took a lot longer to learn because they had never had that experience, and there was blind spots in their experience, and they never learned how to play them? I mean, of course, they don't completely fall apart. So it shouldn't be a surprise, I think, that a learning system with a particular optimization objective, given a certain kind of data, would learn what's there in that data, and if you are a clever scientist, you can figure out where they're going to be broken. So, but that's sort of I'm not sure what to make of that, other than the data wasn't representative of the questions you wanted to ask afterwards. Well, so hang on, Josh. I want to give other people just a chance to talk as well. So I don't know. Go for it.
I would actually change a little bit the angle. Still speaking of success. One thing that I've been wondering for a while in recent years is how to handle cases where humans are not at that high standard that we generally put them. So in everything that I've been hearing about today, we try to replicate humans with the view that those are our role models as, say, computer scientists or even, say, cognitive science. But there are also situations or tasks where actually people are pretty bad at. And so then, if we think about the question that Satinder was asking earlier, how do we know when we got it? It's less clear. And one concrete case is, for instance, figuring out when people are lying. That's something that I've been working on for a while, deception detection. It turns out that people are actually pretty bad at that, and computers can be better than humans. And I'm pretty sure there are many other problems where computers end up being better than humans. And so the question would be, how should we think about these situations when, say, the Turing test is not necessarily a valid test anymore because computers can be better than humans?
That's a great question. I mean, what about those cases where computers are indeed going to be better? The Go player plays Go better than any human at this point. But there are even the earlier versions of chess players play better chess than me. Lie detection is hard for people. What about those cases? What do we learn from that?
Why are you guys fixated on comparing yourself to computers?
Good.
I don't get it at all.
Excellent.
I'm going to just cut off this.
Bigotry.
Particularly because I wanted to mention another problem that hasn't come up, and it seems really important. I call it the problem of the small and the big. And the observation is that life is made up of moments. One moment when we do things, and yet we can only make sense out of it over longer timescales. And how does that happen? Sort of my koan is the special thing about life is that there is a now. So there's one now, and we've got, the only chance we have to take an action is the moment. And yet, our sense of our lives, what's happened in the past, and what we're going to do in the future, they're all larger. Even a momentarily video frame or a momentary sensory input is not a situation and not a state, not an understanding. Everything is larger than the instant, and yet things can only be done at the instant, at the moment. And I think this is a big mystery. We tend to overlook it because we're just all immersed in time and in the flow of data and the signals going in and out. But it's actually the strongest computational constraint to the problem of life, of making decisions, is that it's made of tiny little moments, and we have to make sense of it and plan it in some larger scale.
I'll just say I agree. That's a great challenge. It's part of what, when I was talking about, it turns out we mostly agree, which is good. I much prefer to agree about interesting things than to disagree about uninteresting things. But I think that it's part of what I was referring to when I talked about how minds have to not only model the world, but model our own minds, right? Because you're exactly right. We think and we have to act in the now. But yet somehow we have some cognitive structures that we've somehow built up that allow us to understand that our life is not just the immediate time or place, right? I know I'm here right now with you guys, and we're talking, but I also know there's a whole world out there and a whole universe, and most of the time I'm not thinking about it, but I can think about it when I need to, right? And so the ability to think about our lives and the world and our actions on vastly different scales of space and time, and somehow find our way through our lives in that kind of a world, is a really big issue, and it's one that I don't think any current AI toolkit grapples with.
If I could add on, but is it not also a problem that we expect a 3-month-old to deal with?
I don't think so, actually. I think that's one of the things that 3-month-olds are much. I'd ask the developmental psychologists to weigh on this, but I think that's one thing that 3-month-olds are a lot less sophisticated, probably, than adults, right? And that's probably one of the things that language gives us the ability. Maybe language is, for example, right? I don't know if that's where you're going to go.
No.
I'm happy to say that language is the answer to a lot of problems.
So I have a follow-up question from Matt, from Rich's, which is, several speakers talked about initial state and learning mechanisms. But of course, initial state changes, right? In the now, I have a state right now. So there's always sort of a state now, and then the learning mechanism is going to adapt. So one thing you could conclude from that is that no state is special. That is, our current understanding of the situation is changing, and we're adapting. So why is this sort of obsession, if you like, with the initial state, whatever that is? So I'm curious as to how you think about that. The initial state. Well, yeah, sort of what we are born with somehow, or obsession with understanding that from an AI point of view, anyway.
I find it easier to address that from the point of as a psychologist. Sure. So I think it's important in science not to stipulate what you seek to explain. So a lot of the work that you've done, Josh, is a little bit Necker cube-like to me, in the sense that I spend half my time going, yes, definitely, that is the answer of how we understand physics. And then the other half of the time I go, well, that's just restating the question. Basically you're saying that we're right. You take a model that you know is at least approximately right, and you use it to make predictions, and then you show that people make the same predictions. And so I wonder, when the Necker cube's in that state, I end up wondering, well, but shouldn't we be explaining where this comes from? And that, even if it's innate, then I want to know how the hell could that have evolved? And in addition, I have this, it's just I mean, to some extent, it comes down to what you're personally interested in, but I want to understand how these things are implemented in, like in neural machinery.
I want to understand all those things.
Yeah, no, and I know that's true. I know that's true. So,
and I think that's the path we're on.
well, there's a different answer. There's a different answer, I think.
That's a great reformulation of what I was clumsily trying to get.
I think there's a different answer from the AI point of view, though, which I think for me it comes back to some of the points that Rich was making about what we are in a position to design. I think it's while I agree with you, Josh, that it's worth our while to attend to the startup software, right? Like the things that babies seem to be born knowing something about. Because they are the most fundamental things in our environment, like physics, like the presence of other human agents. It's a little bit convenient at the same time, because it just so happens that those are the things that
More than a little convenient.
Well, no, it's no coincidence, right? But it's convenient in the sense of building models of this stuff, because we already have models of this stuff. We have a model of physics. So here, I'm sitting here trying to formulate a question, and I'm feeling a little stuck between the points that you made, Rich, and then the perspective that you put forward, Josh. I think there's a cartoon version of both of those that I want to avoid. But let me pose the following question. It's fine to think about building models of physics. We can make some progress because we already have a model of physics. How would you think about models of sushi? I took a trip to Japan with my family recently and was astonished at how alien the food was, even given the fact that I've eaten in many Japanese restaurants. Going to kaiseki dinners, you get this sense that there's a whole, science to this. Like, there are rules. There are things that go together and things that do not go together. And some of the things that go together really do not go together for me and my kids. But there's systematicity. You can guess that a kaiseki expert would be able to look at a new dish and tell you, yeah, that fits. That's good. And do you see what I'm asking? How, both as cognitive psychologists and as AI engineers, how can we grapple with domains like that are not, there is some transparency to that. Like, I can tell there's a pickle on top of this plum. I know there are objects there. I know they have different flavors that combine in important ways. But I don't know how to formalize that. So that's what I'm wrestling with.
Brief answers.
Okay, brief answer. I completely agree. That's also my experience going to Japan. But I would call this a part of culture, and I would say to do that, we need to think about the things I talked about at the very end. Basically, learning programming languages. So there's like a language of kaiseki dinners, and there's a language of bonsai, and Japanese culture has a whole bunch of these languages that are very different from ours, and ours has some that are very different from those. Mm-hmm. So going to Japan for someone who grew up in the States is a great way to feel that. And I think that's why I completely agree. Those are not part of core knowledge. They're not part of evolution. We need learning algorithms that can basically build new languages for thinking. And that's a frontier area where people are starting to make progress.
Yeah, that's where we need it.
Okay.
If I could just say one brief thing. So often we sort of think, well, there's the infant's initial state, and then there's what the infant is taught. But part of what culture does is to structure the environment, or language does, to structure the environment that the infant inhabits in a way that passes on information, not through innateness and not through education, but through creating a structured environment, which is one of the achievements of culture. Yeah.
But can I just add to that?
Yeah.
I want to tie that back to the conversation that was just going on about goals. Because I spent many years, I've spent a number of years studying hierarchical action. Mm-hmm. And the really tough problem in learning hierarchically structured behavior is learning the right decomposition, and in particular, learning the right sub-goals. Mm-hmm. Yeah. And after studying hierarchical reinforcement learning for a few years, I'm still completely fascinated by it. I think it's one of the deepest problems that we face, and it relates to the time scale issue too. Mm-hmm. At the same time, I was raising young children, and it occurred to me that most of what I said to them was communicating sub-goals. Mm-hmm. So I'd stand there and I'd say, okay, pick up your toothbrush, and then now put the toothpaste on it. So culture comes in that way too.
Mm-hmm. Yeah.
I'd like more conversation here, but I'd like to prep that we will turn it to the audience in a few minutes to give a chance to ask questions. But go ahead.
I was just going to say that this in a way could be endless. So if we see model of physics, model of sushi, models of, I don't know, me doing something with my 2 kids, and it can get very specific. And even for us as humans, we are not going necessarily to catch that moving target, right? So I will not make a good understanding of, say, sushi, and there might be a number of other things the Japanese will not understand from us. And I'm thinking back at the New Kind of Science big book by Stephen Wolfram, where he was saying number of fractals, and can we understand the simple things beyond those fractals? And I think at some point we'll have to make prioritize things, right? Like, what do we want to understand? What's important? What will take us farther? I mean, is it critical for us to understand sushi or better physics? So, because even for us as humans, I think it can become an endless target in a way, or a moving target.
Good. Show of hands who want to ask questions. Right? Maybe somebody else wanted to type up here. Great. You get priority because you organized the workshop.
Oh.
Okay. So I'd like to question, I'm going to have to walk away from the speakers. I'd actually like to question, I think, the one assumption that received the greatest agreement between Rich and Josh. and I think basically everyone, all of the speakers today, which is that we've got to get our systems to learn models and plan. In some sense that sounds fantastic, of course, right? And maybe they should be causal models, and so we have algorithms for using those kinds of causal models, and so we create problems for our agents of learning those kinds of causal models. We have all kinds of planning algorithms that we can invent. Maybe some of them use subgoals and so on. The question is, of course, planning is one way to use computational resources that process representations that have been acquired from the past. And the question, to use actually Rich's terminology, is whether these planning algorithms are part of the irredeemably complex contents of mind, and that if we actually try to, just take that as a given, that's how we've got to structure our minds, that we're going to be bitterly disappointed, in Rich's sense, down the road.
Well, I think that's a valid question. It might turn out to be that way. I guess I am betting not at the moment, but people often bet on things that turn out to be true. But what you're proposing is to do away with a very, very major component of cognition. In some sense, it's the definition of cognition. Cognition is thought. Cognition is reason. So to me, I translate all those things into planning with the model. Reasoning is planning with the model.
Could you say more what you do have in mind? It's a very interesting question, but what's the alternative you're proposing, or what do you think we should have instead?
The alternative is that it's one of these meta things like Matt talked about, that the algorithm becomes learned, and so it's not part of the initial algorithm, it's something that the network ends up doing.
Exactly. Matt actually,
right, Matt?
Yeah.
It's about deriving the planning algorithm.
Yeah, so I can.
Oh, you mean that we learn our planning algorithms rather than have that come wired in or something? Oh,
Essentially.
okay. That sounds fine to me.
Okay, well, I guess we're all in agreement then. We've done some little toy simulations to kind of determine whether a current network, given a transition function and a reward function, can learn to basically do value iteration, and it works with enough variety. So and we're not the only people who've looked at that. So I was going to say something else, though, and I'm not even sure whether it's connected with that point, but it's related to planning. So I saw you give another talk recently, Rich, in which you said that planning, everything else is subsumed to planning, which I find very intriguing assertion. My intuition is almost the opposite, in the sense that oftentimes when I introspect as I'm planning, what I'm actually doing is very, very much not simulating like doing rollouts, even at an abstract level. I actually have what I think is a good illustrative example. On the way here, I was at the airport and I realized I didn't have a TSA pre-check thing on my boarding pass, which I like to have. And so I went to the Delta desk to complain and say, hey, put that on my boarding pass. And I looked at the length of the line. And I said, oh, that's a long line. And I looked over my shoulder at the security line and I said, how long is the TSA line over there? How long is the non-TSA line? How long is that line? And I without even trying, I said, okay, it's not worth waiting in that line. I'm just going to go to the security. And I don't think I didn't do any future projection in the way that we usually mean that when we do model-based control, when we plan, when we say, well, if I do this, then this will happen. I just looked at the length of the lines. It was more about reasoning. So you look skeptical.
Say, what if I go on that line? How would that be like? What if I go on that line? What would that be like? You thought about the choices and you picked the one?
I don't think so. I just said that line's shorter than that line. Done.
I think it's a perfectly valid
Yeah, it's a perfectly
interpretation
valid
that you did.
heuristic, and I keep smiling because I went through almost exactly the same thing. I also flew here on Delta. They also didn't give me my TSA pre-check. I also, you feel some like, well, I paid all that money for the TSA pre-check, and I waited, okay. And I also looked at this, but the key difference is that I was pretty late for my flight. And I looked at the length of the line to go through the normal security, and I was like, I'm not gonna be able to get there. That's just not going to work for me. And then I looked at the length of the line at the Delta ticket counter and I thought, that's not going to work for me either. So I found a third alternative, which is I saw something that said Delta Premier or whatever, and I went over there and there was no line. And I said, hey, can you give me the pre-check? And they did. And then I got through the pre-check. So I executed a multi-step goal, sub-goal thing.
Yes. Okay. So I think the reason that you're looking at me incredulously, Rich, is you think that I'm saying that people don't plan and we don't have internal models, and I'm not asserting that at all. Clearly, if I were asked how long will this line take, I could answer that question. The high-level point I'm trying to make is, I'm just torn as to whether planning is everything and everything else can be subsumed to it, or whether planning is just a special subset of a much broader capacity which we have, which is just reasoning.
Yes, there's lots of reasons to act. Plans aren't the only one.
Right. I just wonder what the hierarchy is.
I think have a lot to say about this.
Okay, while Rich is answering, any other questions, just raise your hand, please.
Oh, I was just going to say that I am sort of a minimalist. I do like to reduce things to the fewest possible things. And so far, we have planning and we have acting. And among those two, maybe we'll need it more, but maybe we won't. And yeah, let's get another question. Somebody.
And then on this side, after that side, this side.
I have two questions. Hopefully the second one is...
No, one question, please. Please, a quick one. One question, quick one.
Do you think that general AI will arise from neural networks, or is there another medium that should be explored that is more likely to rise to general AI?
Good. Anybody want to take that up?
I have an answer.
Go for it.
Yeah, I'm sorry if I'm hogging the microphone, but I have an answer that I think will satisfy everyone. I think general AI will arise from neural networks, but we will find that those neural networks are computing things that are that are better understood as symbol processing. So neural networks that are implementing basic functions the way that a Turing machine implements basic functions and then operates on a tape you have to interpret what's going on that tape in completely different terms. I think that's where we're going to end up.
I would just add a quote from Bridge that if we were to live in the now, that's what we would say, but in the future we never know, right? So there might be other side.
Okay, Tom, on this side.
So returning to this discussion of the different sort of models that an intelligent agent would need to either have built in or learn somehow, the panelists all seem to agree that there are things like a model of physics where it maybe should be innate, but we understand it pretty well, so that's easy to achieve because we already have accurate models. We also seem to agree that there are things like a model of sushi where we don't understand it very well, but that's fine because it's learned progressively. But what would you guys say about a model of something like morality, which we think should be innate, but we also don't understand pretty much at all with any consensus? And do we have any methods for allowing an intelligent agent to competence we ourselves don't understand.
Good, thanks.
Well, I actually think we do understand a lot about morality. There are various theories. Some of them are pretty good. There's attempts to try to integrate them, like, for example, triple theories, as Parfit calls it. I mean, it's not like we have a single grand unified theory of moral reasoning that everybody agrees with, but there's a lot of progress that's been made, and you can formalize these theories in terms that actually look a lot like the models that we and others have been studying in even young babies. So I just gestured at a few examples of that, like certain kinds of recursive and higher order utilities. I'm not saying that the solution is solved, it's just I think that's a great area of frontier research to make progress on. It is very much, as you say, in between intuitive physics and sushi. And it's also an area where there's surely a lot of, the whole premise of your moral learning workshop that Peter had, which was great, is it is an area where it seems to be there's universals and early emerging and even in infancy, precursors of morality, but there's also clearly a lot of room for learning and cultural variation, much like language also, the insights of linguists there. So that, those are, maybe we should just say, yeah, those are great areas to focus on as cognitive scientists to see the interface of these issues.
Okay, good. More questions from that side. Quick questions would be preferred.
So my question is regarding the physics as well as the sort of algebra representation, the category of agnostic disciplines. So for the game engine, the representations are pretty almost explicit, and you're taking advantage of that. And you said that both is the first approximation, and you can see other ways. So I was curious, what limitation between the physics engine or game engine model, as well as what representation you might be in the future to accomplish?
I don't know how much, I spent a lot of time talking about intuitive physics, so maybe we could just take that offline if you want, but do you want to do that? It's fine. I'll happily talk with you about that afterwards, I'd love to, but...
John, you had a question. Go for it, John.
So you talk about reasoning being, planning being the basis for, I don't know what, but cognition. How about memory? There's many models of thinking that involve recall from memory, and it seems like that has not played a role in many of these models, although we see in some of the more recent work from DeepMind, they actually have explicit memories. I would say that's something that we don't see much from in RL in general, and I just thought I would add that as something to consider for the future, given that's been a huge part of cognitive science for the last 30 years.
Quick response, Richard Matt.
I would just add that I think, well, I won't give a response. It's just thinking of memory as something that we consider computers to be very good at, better than humans maybe in certain ways, just recalling things.
But not in the way we,
right.
Not in the kind of cues we do.
I think there's been a lot of progress in AI on enriching our notions of memory and looking at different forms of memory, especially in the deep RL context. One thing that does frustrate me, though, that I feel we really don't understand yet is temporal credit assignment, meaning how do I learn from very delayed outcomes? And my intuition is that humans deal with that in a way that we're not capturing at all, at least in deep reinforcement learning systems. And so, for example, if I order something on Amazon from some contractor who doesn't get good reviews, but that's okay, and then it comes 2 weeks later and it's damaged and it's not what I wanted, I might think, I'm not going to order from one of those, low-rated vendors anymore. It's not worth it. I'm going back 2 weeks, and I'm probing my memory in a way that's very much guided by my knowledge of the causal structure of the world. That I got this package because I ordered it 2 weeks ago. We simply don't have systems that can span those kinds of delays in that kind of knowledge-rich way.
Anybody has any ideas on how to do that? Maybe one out for a solution.
Well, one thing that's going to be important, I think, that I didn't hear much about is the role that value plays in what we remember, and how we assign value to memories, and to use it as how we search memory so that we get relevant memories.
Go ahead, Rich.
I would just like to basically agree with what John said about memory. It's something we don't really know how to deal with yet, and it's very important. Now, there is some work that's been done recently in deep learning, and I think it's, I wanted to stop and pause on that a little bit, because I think it's a, okay, I'm going to be a little bit
Go for it.
out of turn, or
Go for it.
yes. I don't know that much about the work that's been done in deep learning, but my impression is, so this is an ignorant but still an impression, that they haven't really taken advantage of what we know about memory from psychology and cognitive science. They're kind of winging it and using the words, and we all just use the words. But if we were to be good cognitive psychologists, we would like define, well, what is memory? Of course, there's actually 3-4 different kinds of memory. So we would be clear about what we meant. There's procedural and episodic, and then there's short-term memory and longer-term memory. So there's all sorts of things we're talking about. We tend to lump it all under one word. And as now you're all cognitive scientists, so I should be careful. I'm not saying you guys lump it all under one word. As cognitive scientists, you would be careful about what you mean by it. But all those deep learning neural network computer guys, they just lump things. I told you I was going to get in trouble. So I am just dissing a whole bunch of things that I don't really know much about. But I'd like to try to say it positively. The deep learning guys need cognitive scientists to give them more sophisticated ways of talking and thinking about these kind of topics.
Hey, so on that note, on that great note, that,
he doesn't get a chance.
we will end this. And again, thanks to all the speakers and the panelists.